Welcome to The Explainer. Today we're demystifying exactly how AI creates images. If you've ever typed a prompt into a generator and just marveled at the incredibly detailed, photorealistic image that pops out seconds later, you've probably wondered, how on earth is the computer actually doing that? Well, today we're tracing that evolutionary leap. We'll go from early, kind of clunky methods straight through to the absolute magic of modern diffusion models. We're going to break down the architectural breakthroughs that made all of this possible step by step.
So, let's dive right into this massive question. Because honestly, to really understand modern generative AI, we have to look back at the problem that started the whole shebang. How do you teach a machine to conjure something out of thin air? Or, well, more accurately, how do you teach it to take pure, randomized static and sculpt it into a high-resolution masterpiece? To appreciate where we are right now, we first need to understand the serious roadblocks that researchers were hitting just a few short years ago. Section 1. The limits of early AI. Not too long ago, generative adversarial networks, or GANs, were absolutely the rock stars of the AI world. But if you take a close look at these early outputs, you'll see they're quite noisy, a bit blurry. Honestly, they kind of look like a television struggling to find a signal. The existing methods back then often failed to provide high-resolution segmentation maps. Whenever researchers tried to push these models to capture really fine, crisp details, they just couldn't quite get there. The concepts were a total game-changer, for sure, but the execution was hitting a hard ceiling when it came to clarity and precision.
The reason for that ceiling really comes down to the basic GAN architecture. It was essentially a high-stakes cat-and-mouse game between two networks. You had a generator trying to create fake images and a discriminator trying to catch those fakes. The generator takes random noise and tries its best to make it look like the training data, like the handwritten digits we're seeing here. And while this adversarial setup was incredibly clever, it ultimately ran into those frustrating roadblocks I mentioned. The network simply didn't have the right internal plumbing to preserve the tiny, crucial details from the input all the way through to the final output.
Which brings us to Section 2. Enter the UNet.
To get those truly crisp, high-resolution images, the fundamental architecture of these neural networks simply had to change. Before the massive 2015 breakthrough of the UNet, older models not only struggled with fine details, but they also had an absolutely insatiable appetite for data. They needed massive, heavily annotated datasets to learn anything at all. But the UNet? Total game changer. It offered precise localization and captured high-resolution features beautifully. And the coolest part? It was originally designed for medical image segmentation. That's a field where you typically have very limited data because, let's face it, doctors don't have thousands of hours to sit around labeling millions of cell images. UNet proved you could do way more with way less, provided your architecture was smart enough.
You can literally see exactly why it's called a UNet. The network itself is shaped right like a U. On the left side, we have the encoder. Its main job is to downsample the input image, compressing the data so it can understand the broad context, or the big picture of what it's looking at. But, as you might guess, when you compress data, you lose the fine details. So that is exactly where the right side, the decoder, steps in. It takes that compressed information and upsamples it, blowing it back up to enable precise localization. It basically figures out where those big picture concepts actually belong on the final image grid.
But here is the real secret sauce of this whole thing. To make this work flawlessly, the UNet uses something called skip connections. Imagine you're trying to redraw a highly detailed map purely from memory. You might remember the general shape of the continents. Right, that's your context. But you probably forget the jagged little coastlines. Well, skip connections act like little cheat sheets. They bridge the gap directly from the encoder side straight over to the decoder side, completely bypassing that heavy compression at the bottom of the U. They literally shuttle those critical, uncompressed, high-resolution details straight across, letting the decoder stitch the big picture and the fine details back together perfectly.
Section 3. The forward diffusion process.
Once models like UNet could finally handle image data without losing all those lovely fine details, researchers decided to explore a totally different, honestly kind of counterintuitive approach to generation: diffusion. The forward diffusion process is basically a straightforward set of steps based entirely on destruction. You take a perfectly good, clear image and you progressively corrupt that data. Step by step, you just add mathematical noise. You keep doing this over and over until the original structure of the image is completely gone. By the time you reach the final step, which researchers usually call step T, there's absolutely nothing left of the original image. It is entirely random, pure static noise.
What's really interesting here is the specific mathematical mechanism driving this controlled corruption. It's called a Markov chain. A Markov chain is simply a process where each state depends only on the state right before it. So it doesn't remember what the original image looked like at step 1. It only knows what the image looked like a tiny fraction of a second ago. Think of it a lot like a digital TV slowly losing its signal in a bad storm. First, it gets a little pixelated, then a bit more, until finally the picture's completely wiped out and replaced by pure, independent static.
Section 4, reversing the noise.
Now, you might be wondering, why on earth would we spend all this time and computational power just to destroy a perfectly good image? Well, because the destruction is actually a training exercise. If we can meticulously document exactly how an image degrades into pure noise step by little step, could we teach a powerful neural network, specifically a UNet, to run that tape backward? We want to reverse this forward process. If we can successfully teach an AI to remove the noise at each step, we unlock something absolutely incredible. We gain the power to start with completely pure, random static, and step-by-step generate totally new, incredibly high-resolution images out of literal nothingness.
And this brings us right to the precipice of modern generative AI. We know the architecture we need, and we firmly understand the concept of forward diffusion. But this leaves us with the ultimate cliffhanger for our next explainer. How exactly do we run this process in reverse? I mean, how do we train an AI to look at pure, meaningless static, hallucinate a structure that isn't even there, and mathematically denoise it until it becomes a breathtaking masterpiece? That mathematical magic trick is exactly what we'll unpack next time. Thanks so much for joining this explainer, and keep questioning the technology around you.